One day, I was walking through the store, and because I'm such a nice guy, I was going to buy my students some Jolly Ranchers. And because I'm a teacher, I want to try to save as much money as I possibly can. And I went into the aisle, and I saw these two bags of Jolly Ranchers, which the candy inside them was exactly the same, but the bags were different sizes and different prices. So here I had a 12-ounce bag, pretty small, and it was $3.49. Here on the side, I had a 3-pound bag that was $9.49. And the problem I knew is that I was not getting the same bang for my buck both ways. But I couldn't figure out a strategy to understand which of these would be the better buy. And that right there is learning rates and ratios, which is the skill we're going to cover today. So you're in luck. We are going to answer this question at the end of this video. Before we start getting into some examples with rates and ratios, I think it's important to find definitions for them, and these definitions might be a little bit different than you've seen before. So a ratio is, I will say, is a relationship between two numbers. Now, depending on how mathy that definition is going to get, it can be a relationship between two numbers where you're comparing one thing to another thing, but I'm going to just call a ratio any relationship between any two numbers, which means fractions. When you hear the word ratio, I want you to immediately think fraction. You're going to be dealing with a fraction somewhere, somehow in that problem. Now, rates are the exact same idea of ratios except a step further. So rates are a relationship that compares two quantities, and the difference here is that the quantities must have different units of measure, meaning they can't be the same thing to be considered a rate. So rates is one of those real-world concepts you use all the time and don't even realize it. If you're ever in a car and you want to see how fast your car is traveling, you do that in miles per hour. That's a rate, or that's a speed. Whenever you walk into a classroom and you see that there's 21 students, that's going to be students per class. And if you're ever buying Jolly Ranchers at the store and you want to know how much it costs per ounce, that'd be dollars per ounce. One final thing before we move on from this slide. Right here, when I say dollars per ounce, okay, the word per means division. So anytime you say per, miles per hour, students per class, dollars per ounce, that means the first number divided by the second. If you bring me this page with these two very important concepts written down in your notebook, I will give you one piece of candy. So let's do some real-world examples where we can use ratios to help us solve problems. So Mr. Reed has decided to start a China tennis team. That's exciting. Tennis is pretty awesome. The only problem is that tennis balls are really expensive. Well, and if you hit tennis balls like Mr. Schmidt does, that means they're going to be going over the fence and they're going to be gone forever. So he needs to save as much money as possible. So he goes to the store and he finds 3 sets of options. These tennis balls are all identical. We need to know which is cheapest. So when we think about problems like this, we want to think about, okay, so we're doing a ratio. We're going to divide these two numbers. Do we want to do tennis balls per dollar, or do we want to do dollars per tennis ball? And I'm hoping when you say it out loud, you understand that dollars per ball makes more sense than balls per dollar. Okay, because balls per dollar would be telling you how many balls can you get for a single dollar, which would be a little odd since you're going to the store and the number is already set. So we are going to do dollars divided by the number of tennis balls for each problem, which means we're going to be doing some long division. So for the first problem, we get $7, and we are going to divide by 6 tennis balls. So going a little quickly through the long division here, because I'm hoping that you've done enough long division before. If you need any help with long division problems, it's been a while, you need some review, please, by all means, come and talk to me. So if you notice, it's money, so we're going to round to the hundredths column, which is right here. But in order to round to the hundredths column, we have to go one digit past it, which means that this is going to round up to $1.17 per ball. And now I want you to finish the other two problems here to see how expensive each ball is, and then figure out which is the cheapest. So as you notice, the middle one is actually way cheaper than all of the others. Therefore, the middle one would be the option that Mr. Reed should pick to save the most money. Just a few quick other things when we're talking about finding unit rates. So unit rates is really breaking down the denominator so that it's 1. So if we notice in this first problem, it's 42 apartments per 3 floors. In order to be a unit rate, the denominator must be 1. And that may sound a little confusing, but the reality is it's thinking of the problem the way that you probably wanted it to be in the first place. So you wouldn't drive in a car and say, I traveled 200 miles in 4 hours. You'd say, I drove 50 miles per hour. And that's what a unit rate is. So for this first example, we would do 42 divided by 3, which is 14 apartments per floor. 10,000 steps per day, which is what my wife actually has on her Fitbit. When she wanted to know how many steps she did per hour, well, a day is equal to 24 hours. So I would do 10,000 divided by 24. To keep the video nice and short, I just sped through the long division over here. So we get approximately 417 steps per hour. And since we rounded, we need to use the magic math word about, that we are not exact. So then 192 students in 4 grades. We do the exact same thing. We do 192 divided by 4, which would be 48 students per grade. Another word you might see here is on average. And we've probably done averages before in math, but when you're doing unit rates, you're probably doing averages as well. So now I think it's time for us to go back to that original problem and figure out which of those bags would be better for Mr. Schmidt to buy. Now, if we notice right away, these labels are not the same. And so I was actually kind enough to go search out the conversion rate between ounces and pounds. So it tells us that 16 ounces is equal to 1 pound. So I can either convert this to pounds or I could convert this to ounces. Since this would make a fraction, I'm probably going to convert this to being 48 ounces, which means I would do either ounces per dollar or dollars per ounce. And I'm hoping that we understand that most people are going to choose dollars per ounce to get this answer. So I want you to do the long division and see which of these ends up being cheaper. And after doing the long division, I realized that the bigger bag was actually cheaper by about 9 cents per ounce, which makes a pretty big difference considering there are 49 ounces in that bag. And that right there is the basics of ratios and rates. As always, if you have any questions, please let me know. There should be options for you ready to go on the choice board.